Now just start sharing.
Yes.
You should be in the answer.
I should be the pleasure to have Professor Meena Mahajan, friend of the institute. He has been with us, visited us several times in the past. She works very broadly in computational complexity theory and has generated many studies, many influential studies. So I'm very happy that she's going to give the talk. She works in Boolean, proof, actually all of complexity theory, arithmetic complexity. And today she's going to talk about proof complexity.
Thank you, Arshad. It's very nice to be known as a friend of TR. Considering that we're just discussing rival setup. Is this an okay place to see?
You can stand there.
But am I blocking the view of the screen for those who are in the room?
No.
Yeah. So I'm going to talk today about there's what I think looks like an intimidating title. It would certainly have been intimidating to me 10 years ago, quantified CDCL dependency schemes. And actually, I'm going to spend most of the time in the talk explaining what it is about. The actual results will come at the very end, and maybe not much time will be spent on that. Okay? So this is, like Arkadev said, this is work in proof complexity, but even proof complexity, most of the active research now is happening in the area of propositional proof complexity. That is, this work is to do with QBFs. And it's a much smaller community. It's growing, but it's a much smaller community which is doing QBFs. So this is, was there a question? No. Okay. So this is work which I've done with Abhimanyu Chaudhary, my most recent student. He defended his thesis just last week. And all basically I'm giving the kind of talk that he gave last week at his defense. Okay, so solvers and proof systems. So QBF solvers, I'll come a little later to what QBFs are, quantified Boolean formulas, because I need a particular format in which we will address them. But right now, at a higher level, QBF solvers are algorithms. I mean, for some reason in this community, they are called solvers. Okay? SAT solvers, QBF solvers. These are algorithms which try to decide, in the case of SAT solvers, they're trying to decide whether a formula is satisfiable. In the case of QBF solvers, a QBF is either true or false. It's not satisfiable or unsatisfiable, true or false. And they're trying to decide whether it's true or false. And QBF proof systems are actually formal systems in which one can reason about the truth or falsity of QBFs. And so they will have some specific syntax, some specific rules, reasoning rules that could be used. And the idea, the reason why we are looking at proof systems at all is that they, in some sense, they abstract out the reasoning that is actually being used in algorithms. So various kinds of solvers, they have different reasoning rules which are not explicitly stated in the algorithms, but the algorithms rely on those. And the proof systems are making this explicit. That this is why the solver proceeds the way it does while not giving a wrong answer. So they're abstractly modeling this reasoning, and in a particular proof system, you can talk about how long is a proof of the fact that a QBF is true or a QBF is false. And if you can prove somehow that the shortest proof must be very long, then that would imply that any solver which is using this as its basis for reasoning must require a very long time on that formula. Because implicitly in the trace of the algorithm, there is a proof in the corresponding proof system. So that's why we're interested in lower bounds in proof complexity. Here's one specific solving approach, QCDCL, which appeared in the title. It's not one solver. It's a kind of paradigm for trying to solve, try to decide the truth or falsity of QBFs. And there is one specific reasoning aid, which is called dependency schemes.
So there is no probability here. It's either it's correct or incorrect.
Either it is
correct or incorrect. There's no randomization.
Usually there is no randomization. There is randomization in some of the solvers which are for instance in the propositional world that we are just trying to decide SAT. All the SAT solvers that I know of, essentially all of them are deterministic. There are randomized solvers which are not doing SAT, but they're doing sharp SAT, model counting. So you have to do approximate counting, randomized. But most of the standard SAT solvers are deterministic, and the QBF solvers, which have been developed in the last 10-15 years, are also deterministic. So dependency schemes are one specific reasoning aid that have been analyzed from a proof-theoretic point of view in the last 12 years or so, because there was one solver which decided to use it. So one solver came up with this idea, one set of designers of one solver, they came up with the idea of exploiting this particular heuristic, and then proof theoretically it had to be analyzed. And now we are at a stage where proof theoretically we know a fair amount of about how these dependency schemes affect the length of proofs. But unfortunately, that still does not tell us enough about how the dependency schemes actually impact solving. There we don't know enough, and the two seem contradictory, because I said that the proof systems are describing what goes on in the solver. So the real problem is that we have known proof theoretic lower bounds, but they are not for the right proof systems. So there are proof systems which exactly model the solvers. There are proof systems which are describing something somewhat related, and we have lower bounds in the related proof systems, but not in the precise proof systems, which capture this.
Did you already mention what a dependency scheme is?
No, not yet. Not yet. So this is, we are still in the very high level thing, that there are algorithms, there are heuristics that they use, there are proof systems which we use as a way of analyzing or giving lower bounds on the runtime of the algorithms. So the QCDCL-based algorithms, that's one family solvers, that's one family of algorithms. Dependency schemes is one particular heuristic. And now we want to see proof theoretically how we can analyze. And like I said, what we already know about it is not in the right model. So therefore, clearly the questions to be asked at this point is, what is the right proof system? If I want to understand QCDCL solvers and I want to expose their limitations, what is the proof system that I should be analyzing? And of course, before getting to that, we need to know what dependency schemes are. So I'll take these questions in the reverse order. Let's first start with what are QBFs and what are dependency schemes, and then try to understand what the proof systems are. Okay. Yeah.
What is being quantified here? What is quantified?
So we have a quantified Boolean formula.
So the quantified refers to that.
Yes.
Not to the conflict.
No. So, so the reason why the quantified has appeared there is that conflict-driven clause learning is a paradigm which has been used extremely successfully in SAT solvers. So as theoreticians, we of course love to say satisfiability is NP-complete, hard problem, do something else. And if you ask any practitioner worth is solved, satisfiability is solved problem. If you can reduce your thing to SAT, you're done. Okay, SAT solvers are working fantastically on practical instances which are arising in whatever applications there. And there was a very clear transition, flipping point where SAT solvers went from being somewhat okay to fantastically good, and that was when they started using conflict-driven clause learning. And this year, I think it was this year, would be exactly 30 years since the first CDCL SAT solvers, Sakala and Marcus Silva. And then there was another group which quickly followed up on it. So CDCL in satisfiability is very well, by now, a very well-known, well-studied paradigm. And then how to use it for QBF, so the quantified use.
Okay. Quantified is not quantifying CDCL here.
No. Quantified version of CDCL for QBFs. Okay, so what are QBFs? I'm going to do QBFs and resolution quickly. These are the propositional versions, which were resolution. So what do I mean by QBF? A QBF is a quantified Boolean formula. So we are starting with a Boolean formula. And normally when you think of satisfiability, you think of a formula which looks like this. You have, let's say, CNN SAT, conjunctive normal form SAT. So you have a bunch of clauses in some of these variables. We are going to look at quantified versions. So all these variables have to be quantified as either existential or universal. We are going to assume that every variable is quantified, so it's totally quantified. All the quantifications appear right in the beginning. This is not necessarily the case. You could write formulas where you have quantifications inside, and that could make the formula more succinct. But we are going to look at this case. The formula is in prenex form. And the inner, so totally quantified in prenex form, and the inner propositional formula in CL. So it looks, this is a sample formula. Okay. So you can see that we're not asking a question about satisfiability. This is a statement which is either true or false because there are no free variables. Either there indeed does exist an E for which no matter how you choose you can choose a C, D to satisfy all clauses, or there does not. And the solver has to decide which it is. So most of the QBF proof complexity literature is going to deal with this normal form only. Solvers also very often start with CNF versions and then try to determine truth or falsity. Now here is a specific inference rule, resolution, which says that if in my inner formula, which is called the matrix in this community, if in my matrix I already have clauses which look like X or A, negation X or B, then I can derive the clause A or B and add it to the matrix. And doing that is not going to change the truth or falsity of the QB. So it's completely clear that adding any clause, not just a clause through resolution, adding any clause is not going to make a false formula true. And you could not even satisfy the existing constraints. If I add more, you cannot satisfy them. Okay, but it could make a true formula false. And what we would like to understand is when adding clauses through resolution is okay. So if I had a false QBF which had only existential quantifiers, then I could just forget about the quantifiers and say this is an instance of SAT. SAT is exactly the special case of QBF with no universal quantifiers. So if I have such formulas, then satisfiability instance, okay, only existential quantifiers, then just by repeatedly using the resolution rule, I'm guaranteed to be able to eventually derive the empty clause. And that would be viewed as a proof that the formula is indeed unsatisfiable. Because if inside this matrix somewhere there is an empty clause, there is no way you can satisfy. Right? So the fact that repeated resolution allows us to derive the empty clause, we would say that resolution is complete for satisfiability. But now what happens when you have this universal quantifier? So with the universal quantifier, resolution alone is not going to be enough. You need one more rule, or you need a different way of approaching it. But the most standard way is to use this so-called rule called the universal reduction rule. And what the universal reduction rule says is that if I already have a clause in which there is a universal variable, it could be negated or unnegated, there is a universal variable, but all other variables hanging out in that clause were quantified before this variable. Remember, the quantifier prefix has an order amongst the variables. So if all the other variables were quantified before this universal variable L, in that case, I can drop that universal variable altogether and produce a shortened clause and add it. Again, adding the clause is not going to turn a false QBF into true, but we need to reason that it, if the formula were true to begin with, it will remain true even after adding this clause. And in fact, that is the QU resolution proof system, the first generalization of resolution for SAT to a QBF proof system. It has exactly two rules: resolution, universal reduction, nothing else. And in this system, a proof that a formula is actually false is to use these two rules, resolution, universal reduction, repeatedly, keep deriving new clauses until you finally derive the end clause. So again, as in the case of satisfiability, every false QBF, it does have a proof of falsity in this system. The system is complete. The system is also sound. So by sound, we mean that if indeed there is a proof in this system, then the formula is false to begin with. Through formulas, you cannot end up deriving the false clause. It's not very hard to see why it is sound, but I'm going to briefly describe why it is sound because that is going to naturally lead us into where we can tinker with something and use a different heuristic, and that's where dependency schemes come in. So to understand soundness, it's nice to do it via this evaluation game, which again, many of you may have already seen in the context of QBFs. The way to read whether a QBF is true or false is to imagine that there are two players who are stepping through the QBF trying to satisfy the inner limits. So there's an existential player who owns the existential variables. There's a universal player who owns the universal variables. They step through the prefix in the order of the prefix and assign values to the variables they own. Then by the time they reach the end of that prefix, all variables have been assigned. So the inner formula, which was purely propositional, it's either true or it's false. If it becomes true, then the existential player has won. And otherwise, the existential player has lost. So this is like reading out the formula in English. We wrote the formula using these logical connectivities, but if you like the way I read it out, there exists a value of E so that no matter how U is chosen, the existential player is asserting that there exists a value, and if he or she chose that value accordingly, then indeed the inner formula should finally be satisfied. So one particular run of the game would be won by the existential player if the matrix on that run is satisfied. But the existential player has a winning strategy if no matter how the opponent plays, he can always win. Okay? And well, this is a fully determined game. Exactly one of the two players always has a winning strategy. So one could think of the solver as trying to figure out who has a winning strategy. That's the same as trying to figure out whether the QBF is true or false. So now the rules that we put into that proof system, QU resolution, these are very sound rules. What do I mean by super sound? Suppose remember, we don't have to prove that it preserves falsity, right? Adding clauses, if something was false, it remains false. What we would like to prove is, what we need to prove is that it preserves truth. And this is what I mean when I say that these rules are super sound. If the existential player had a strategy to win, that same strategy would also be a winning strategy after I add a clause. I add a clause using either of these two rules, either resolution or universal reduction. So that same strategy continues to be a winning strategy. But eventually, after I add several clauses, I've added the empty clause, and we know that for the empty clause, there is no possible winning strategy. So therefore, there could not have been a winning strategy to begin. Okay, so why is this reduction rule sound? Why does it preserve every winning strategy? Because again, if you think of it in terms of the game, if I have a clause which looks like A or L, L is this universal variable, everything in A was quantified before L. And the game is being played by these two players. It's now the time for the universal player to play L. By that time, if A has not been satisfied, the existential player has lost. The universal player is not going to be kind and say, okay, let me set L to satisfy this clause. The universal player is an adversary as far as the existential player is concerned. So if the existential player has any hope of winning, it must be by satisfying A before L has been reached. And therefore, adding the clause A is also found. The same strategy which worked earlier will now work. You don't even need to modify anything in that strategy. So in some sense, this universal reduction rule is implementing what I call a super sound adversarial instantiation of the universal variable. If the universal variable is instantiated in the adversary in a most adversarial way, even then this rule remains sound. And now at this point, if you have been figuring out what's going on in the game, this question should arise that super soundness is an overkill. So how did I define super soundness? It preserves every winning strategy. I want to make sure that if the formula was true before I used a rule, it remains true after I use the rule. But it remains true if there is even one winning strategy. I don't need to preserve every winning strategy. So super soundness is definitely an overkill. What we would be happy with and satisfied with is a sound rule. So ideally, what we would like is to understand when is an application of the reduction rule sound. I want to change the definition of reduction. I should be allowed to remove universal variables from clauses even if they are not rightmost. I have some guarantee that removing this universal variable from this clause and adding a new clause is sound. By sound, I mean it preserves at least one winning strategy, assuming there was a winning strategy to begin with. If there was none to begin with, then you don't have to do anything. But we don't know a priori whether there was one to begin with or not. So we have this kind of implication that we would like. It should preserve at least one winning strategy, if at all one exists. So can we stare at the formula and at the clauses and try to figure out which reductions are sound and which are not? Now, again, a little bit of thought should convince you that this is a semantic requirement. Right? I mean, it's not something that you're looking at the syntax, the structure of the clauses and how they interact. So either there is a winning strategy or there is not. So logical equivalence we are trying to preserve. So this is a semantic requirement, and testing semantic truth is the problem of deciding QBF truth. I mean, that is the piece-space complete problem. So we're not going to be, we should not expect that we can examine every potential application of the rule and quickly, efficiently decide whether that is sound. In general, this is not going to happen. We want ways of doing this efficiently.
So, and throughout this, we are only going to keep adding clauses to the matrix, right?
We are only
going to, okay.
Yeah. So, in the QBF solvers are still not advanced enough. They are not yet doing forgetting. Okay. The SAT solvers, there are advanced SAT solvers which also forget clauses because keeping too many clauses around then slows down everything. So this is, I mean, I've been also listening to many more talks from practitioners and SAT solvers where, we think of polynomial time and they say, oh, this is 2.5n, that's too slow. And I want to take 1.1n or something. So yes, they frequently forget clauses, but the QBF solvers, as far as I know, have not yet gotten there.
So for sound, I would have actually had even a weaker definition which says if there is a winning strategy before, there exists a winning strategy after. Whereas you're
not be the same one.
Yeah, it needs. But so I'm asking if winning strategy afterwards is actually one of this one. Is that a stronger requirement or this is without loss of generality?
I think I cannot give an example.
Is this only without loss of generality or?
No, I don't understand this.
No, because these reductions are only adding clauses.
Right.
Therefore, is this without loss of generality? No, you're playing. Sound has a definition. Sound means if there was a winning strategy, before there's a winning strategy after.
But this is so if we are only adding clauses, then it is also true that what is a winning strategy after adding the clause was a winning strategy to begin. And therefore, one being preserved is without loss of generality. If you do addition and deletion of clauses, then things could change. But here, if you can win after adding the clause, that same strategy would win early. So this is a semantic requirement which we don't expect to be easy to test on the fly. But it turns out that there are some syntactic conditions on the matrix. So you can examine the matrix, well, not just on the matrix, also on the prefix. So some syntactic conditions on the matrix and on the prefix, if you look at them and you can quickly test them, and if they are met, then they would guarantee this semantic requirement. And dependency schemes provide such tests. They are not the only such tests, but they are a test of this form. So they provide a mechanism to look at the formula and to figure out which reductions, even though they don't follow the standard universal reduction rule setting, are still sound to apply. Okay, so to understand what dependency schemes are, the general framework is like this. I start with this formula on top. Like I said, all the variables are quantified in the beginning, and then there is some inner CNF formula. The usual universal reduction says you disallow reducing xi from a clause C if there is some xj in the same clause, either xj or negated xj, for a j greater than 1. There's some variable to the right of xi which is appearing in the same clause. Then you are not allowed to throw away xi. Right? And this is what we saw was super sound. So this is super safe. In some sense, this is an over approximation. So here, implicitly, what we are saying, oh, xj appeared after xi. Xj depends on xi. So if xj depends on xi, you cannot reduce xi. Xj is hanging out there blocking this reduction. And so here is the trivial dependency, what is called the trivial dependency scheme. Xj depends on xi as per the prefix order if xj appears after xi. And usually you would assume xj appears after xi and is of a different quantification type. Because if it's owned by the same player, then you can always take that into account. So if there is an opponent variable which is coming after you, then that variable will block. So this is what is called the trivial dependency scheme. What is it? So in general, what does a dependency scheme do? For each formula phi, it picks a subset of these pairs. These are ordered pairs. Xj depends on xi. Okay, and the trivial dependency scheme picks all pairs according to this order. A non-trivial dependency scheme would pick some subset of this. Some pairs it will throw away, saying these are not necessary for preserving soundness. Okay. So this is the universal dependency.
Are just saying that you're not even looking at psi at this point. It's just looking at.
For the trivial dependency scheme, I'm only looking at the prefix.
Yes.
If j appears after I, then xj depends on xi.
Okay.
Now, for a non-trivial dependency scheme, I will look at this as well at psi and then try to pick out a subset of this which can be thrown away and retain only a smaller set. And if I am able to do that in some way, then let's say that D has picked up some subset of these variables, and then I am allowed to derive A from A or L. That is, I am allowed to throw away L if all the other variables which appear in A don't depend on L according to the subset that D has picked. So there could even be in A variables which are quantified after L. But if this dependency scheme D as applied to this formula has told me that those variables don't depend on L, then it's safe to allow this reduction of it. So the question is, what kind of dependency schemes would do this? Like I said, I think it was 2013 or 24, around then that the first QBF solver which actually used dependency schemes came about. And it used a very simple dependency scheme which they call the standard dependency. So you construct a graph where there is a node for every variable. You connect two nodes if those variables both appear in the same clause. If there's any clause containing both x and y, then there is an edge between x and y. And now you say that xj depends on xi if, first of all, xj should appear after xi. If it appears before xi, there is no way it can depend on xi. So it will depend, xj depends on xi according to the standard dependency scheme. If it appears after xi, and in this graph, if I keep only the subgraph of variables xi and to the right, I throw away all the variables to the left. In that subgraph, there should be some path from xi to xj. In fact, they do something, no, so I think I'm missing one. I keep xi and I keep only the existential variables to the right of xi. Xi is universal. I'm trying to figure out whether I can drop xi. I keep only xi and the existential variables right of xi. And now I check, is there a path from xi to xj? Now, the fact that you're throwing away those other universal variables, that makes it a bit mysterious. Why is this still sound? And so it was, I think 3 years later, in 2016, first there was a formal proof that this reduction rule using the standard dependency scheme is indeed sound. And then
Where did phi come?
where did what come in?
Oh, yeah.
The graph.
Graph.
The graph looks at the clauses.
Yeah.
Right. So, like I said, the dependency scheme was first used in a solver around 2013. The first proof of correctness of this rule came about in 2016, and that same proof also defined some much more complicated dependency scheme. So, there is a dependency scheme called reflexive resolution path scheme. I'm not going to go through the technical definitions. I mean, what I want to convey here is that it is a dependency scheme basically picks a subset of this. How it actually does this is not so important for the contributions that I want to describe. But more complicated schemes were described. And I'm going to look at 2 of them, D standard and this reflexive resolution path scheme. As far as I know, these are the only 2 dependency schemes which have actually been used in solvers. Many more powerful dependency schemes have also been defined. But when would a dependency scheme be more powerful? If it throws away more pairs. Right? The smaller the subset it keeps, it's enabling more reductions. And enabling more reductions seems like a good thing because finally we are aiming to reach the empty clause. We are trying to prove the QBF is false. We're trying to reach the empty clause. So the faster you can throw away things, the better.
But I think these things could be incomparable, right? I mean, like for some particular phi, one might be more efficient than the other. And,
Right. But in general, suppose I tell you this this kind of a statement. I have 2 dependency schemes, D1 and D2. And for every phi, D1 of phi is a subset of D2 phi. Then you expect that D1 is strong. Right? So it turns out that the D standard is always a subset of D trivial by definition. Anything has to be a subset of D trivial. DRRS, that reflexive resolution path scheme, is always a subset of D standard. Sometimes it's a proper subset, sometimes it's not a proper, but it's always a subset. So you would expect RRS to be strong. Okay, so this is what dependency schemes are about. So QBF, we saw QBF, one standard normal form formulas, and QBF proof systems, we saw one resolution universal reduction, we saw a dependency scheme. So now we have to come back to CDCL. But before that, maybe I should do one concrete example of this, what is sound, not super sound. So remember, to show something being sound, not super sound, if I have to give an example, it had better be an example of a QBF. A false QBF, you do whatever reduction rule, it will remain false. Whereas here, to show, here is an example of something which is sound but not super sound. So there should be an existential winning strategy which vanishes after applying the rule, but some other winning strategy continues. So here is the formula. I hope you can all quickly see that this formula is indeed true. Okay. There exists x1, so that no matter how u1 is chosen, there exists an x2, so that both these clauses are satisfied. It's true, the existential player has a winning strategy. In fact, the existential player has multiple winning strategies. Okay, here are all the strategies as far as I know. The existential player could start off by setting x1 to 0 or x1 to 1, and then the universal player can choose in whatever way. And then what can the existential player do? Either the existential player can say that x2 should be the same as x1, both clauses will be satisfied, or the existential player can say that x2 should be the opposite of u1, again both clauses will be satisfied. Now if you look at the trivial dependency for this formula, then according to that x2 depends on u1. And u1 depends on x1. Yeah? These are the trivial dependencies. So x2 depending on u1 is part of the trivial dependency, but I claim that removing this pair is also sound. If I completely remove the pair U1, X2. I claim that X2 does not depend on U1. What does that mean? That means that in the evaluation game when they are playing, the existential player has to choose the value of X2 without even knowing U1. But this is not a problem. We still have a winning strategy. The first two strategies did not require X2 to know what is the value of U1. So it still preserves 2 of the 4 winning strategies. Okay. So a dependency scheme which after staring at this formula says that this pair is no longer a dependency would be sound. And using that for this reduction would be sound. That's what I mean by trying to stare at the formula and figure out which reduction rules are sound. Okay. Oh, so this is the first part, explaining what these dependency schemes are. What do we know about dependency schemes? Well, the first line I already mentioned orally, RRS always produces a subset of standard, which always produces a subset of trivial. For many schemes, in particular for standard and RRS, in fact, there is a whole family of schemes called the normal dependency schemes. They are known to be sound. And therefore, they can be used along with resolution. So I said initially we started with resolution or resolution and universal reduction. Now I can say resolution and universal de-reduction. And that would also be a sound system. In fact, there is another variant called long distance Q resolution, which again I won't describe here, but there is such a system. And even in that system, I could use de-universal reductions instead of just universal reductions. And in all those cases, for many schemes, we know that the resulting systems are sound. But not only are they sound, they can dramatically shorten proofs. So for instance, in that first system that we saw, resolution plus universal reduction, there is this family of formulas which has theta n variables, theta n clauses. And probably we know that any proof in this system requires size exponential in n. But the RL scheme examines this formula and says there are no dependencies whatsoever. And the moment you say, okay, there are no dependencies, then a whole lot of reductions get enabled right in the beginning. And after that, there is a linear sized proof. So proof size can reduce a lot if you are allowed to use a de-reduction as opposed to the standard, the standard is a loaded word, as opposed to the ordinary universal reduction. And it can have an exponential. So it's making this difference in QU resolution. Now the question is QU resolution the right proof system to understand what is happening in a solver? And like I argued earlier, that is not the case. So we need to.
Sorry, I just want to understand. So the solvers, I mean, is it the case that what ends up happening is like you inspect the formula psi and then figure out what is the
dependency?
What is the dependency? I mean, how much can you prune down the dependencies? Oh, and then you use QU resolution with these dependencies to generate new clauses and try to find the.
So a solver does not use QU resolution. QU resolution is the abstraction. The solver is an algorithm. It's not directly using QU.
Okay. I see. Okay.
No, but if you prove a lower bound on the length of the QU resolution, will it prove a lower bound on
it will give me a lower bound on a certain kind of solver. But those solvers are not yet implemented. So there are solvers of a particular kind which make certain design decisions, and from those you get what is called long distance Q resolution proofs or Q resolution. So Q resolution is a subclass of QU resolution, which I have mentioned here. I haven't mentioned here. Maybe it's on a later slide. QU resolution is a subclass where even when you do resolution A or X and B or not X, that X must be existential. You're not allowed to do resolution on a universal variable. So most solver runs will give proofs in either QRes or in LDQRes. So if you can prove lower bounds there, then you're good. But the equality formula, yeah, actually that's a good example. The equality formulas are hard for Q resolution, and the moment you apply DRes, then the proof size, this is not QU, this is just Q. All the universal variables just go away. So all your resolutions are using only existential variables. So it does give solver runtime lower bounds. Okay, so the question is how to exploit this in specific in solvers which are using the CDCL paradigm. So for that now we need to see what is CDCL. So like I said, CDCL is conflict driven clause learning. It was the breakthrough paradigm which completely changed SAT solving 30 years ago. And what has been happening in the last 15 to 20 years is adapting that to the QBF. So I had some slides earlier which described how it works for SAT and then how to adapt it to QBF. But now I'm directly going to start with the QBF setting, and I hope I can make myself clear. a QCDCL style algorithm, like I said, this is a style of algorithm, so paradigm. It tries to follow the perspective of the existential player. So I'm just as a matter of convenience sticking to the situation where we are trying to prove that a QBF is false. What the solver is actually going to do is it's going to try and search for a winning strategy of the existential player. It's similar to what the SAT solvers do. Given a formula, they try to search for a satisfying assignment. Do backtracking where necessary. Keep searching for a satisfying assignment until at some point you peter out and you say there are no more options to explore. It is unsatisfiable. But you're searching for a satisfiable assignment. So a satisfying assignment. So similarly here, you search for a winning strategy of the existential player. So to search for that, what do? When you examine the matrix, if there is a unit clause, you must set it to true for the existential player to win. So if there is a unit universal clause, you have lost. But if there is a unit existential clause, set it to true. That may then make some other clause which was not unit, now unit. You have to set that to true. So there are these what are called propagations. Then you reach a point where there are no more propagations possible, but still the formula is non-trivial. Then you arbitrarily pick some variable. Okay, let me try this. Think of a backtracking algorithm. Okay, let me try this. So that's a decision. You pick a variable to decide on, you pick a value to assign to that variable, you decide. Now that may trigger off some more propagations. So you keep going through this decide, propagate, until at some point some clause gets falsified. Then what happens as a result? You don't just backtrack. So in a backtracking algorithm, you would at this point say, okay, let me try something else. In a clause learning approach, you would say, okay, if I were to follow this assignment, something gets falsified. This is useful information. No? It means that this combination of literals is something which I should not use in a winning strategy. It's not winning. Okay. So somehow I need to use that fact. So whenever the clause is falsified, you learn something that should be avoided in this strategy. And there is a specific learning process which from this trail of decided and propagated literals does some backward resolution. Sometimes it does backward long distance resolution and it comes up with a clause and says, okay, this clause I can add to the initial formula, truth and falsity are preserved. So from the perspective of the existential player, arbitrarily deciding variables but propagating wherever absolutely necessary, that will, if it leads to a falsified clause, a conflict, then you learn something from it. So that is the conflict driven learning of a clause. But suppose I follow this trail and all clauses are satisfied. If this were a SAT solver, at that point it would say I'm home. I know the formula is satisfied. But this is QBF. So one particular run you have satisfied, that doesn't mean that the QBF is true. It just means that this is a good trail. If I were to construct an winning strategy, I can try and use this fact. So I should learn something from that also. So what the existential player learns something to aspire for as opposed to something to avoid. And that is learned by adding a disjunctive term. So at any intermediate stage, we start off with a formula, inner formula, which look like a conjunction of clauses. But at an intermediate stage, you may add more clauses here to this conjunction, or you may add a disjunction here. So every trail that you try out ends with some kind of conflict, as a result of which you either put one more constraint here or you put one more term here. And then when does the solver finally know that the formula is false? If at any point you add an empty clause here, the formula is false. And at any point, if you add an empty term here, then you know that the formula is true. Because the empty term can never be falsified. And then this inner formula becomes true. So this is how most solvers run. They are doing this decision and propagation and learning. And for each one of these, of course, there has to be some specific process by which you decide which variable to decide, which value to assign to it, how to learn a clause. And I'm not going to go into the details of that. So what are the...
I don't quite follow this part. So suppose you don't find a conflict, then why does it mean you have a term? Because you have those universal variables that you did not assign here.
Well, the solver assigns all variables.
Okay.
The solver has to assign all variables, typically in the order of the quantifier prefix. It will try out values where they are not forced. Propagation will be done only on existential variables.
What is propagation?
Propagation is, if I have a unit clause, I must set it to true. I must set the variable in that to true. But if that unit clause is a universal variable, then I don't set it to true, because that is the prerogative of the existential player.
Okay.
So this is something that does not arise at all in the propositional, when you're dealing with SAT. It's specific to QB.
Personal variable, then maybe.
You have lost. You have lost. You have lost on that run.
Okay. No, that is.
Yeah. So if there is a universal clause, then the solver, if it wants to speed up things, it should quickly set that universal variable to false. But that is not counted as a propagation. That's counted as a decision. The solver decided to choose this, and so on decisions you can backtrack. On propagations, there is no question of backtrack. So there is this difference between decisions and propagations. Okay, so the policies used in our QCDCL solvers, I'm describing the policies over and above those which would be used in a CDCL solver. So CDCL, there are no universal variables, and whatever the SAT solvers are doing, over and above that, what is new that we need for quantified formulas? Well, the decision policy, how to choose the next decision variable when there is nothing unit hanging around. This is a question even for SAT solvers. But all the variables are existential. Here now there is this interplay, existential, universal, and you think of the evaluation game. So you should not be allowed to decide a variable if things before it are not yet assigned. So that is what is called level order. Okay, usually it respects the level order. So level order says that if this is a universal variable, I can decide it if all existentials before it have been assigned. They may have been assigned because of earlier decisions or because of earlier propagations. That doesn't matter. But if there is an existential variable before this which is yet unassigned, then I'm not free to assign this universe, decide this universe. Same thing for existential. So that is what is called level order. But the solver which actually first used dependency schemes broke this order. So the decisions were not always respecting the level order. It used a dependency scheme there. And that was very radical, that how can you expect soundness if you're doing this? So that's why it took 3 years before a formal proof of soundness came about by a different set of people. The other policy that you would need to use is reduction propagation. When is a clause considered unit? I mean, I just described, if the clause is unit, you set it. But in the QBF world, there are clauses which are pseudo-unit. I may have a clause which looks like X or Y or U. And maybe X and U are universal variables. And Y and U are universal variables. By applying the universal reduction rule, I can remove them, and then this becomes unit. It's X. So a clause may not be unit just looking at it, but if after applying the reduction rule it is unit, then you have to propagate that X. Otherwise, again, the existential player would have lost. Okay. So what is considered unit? Usually, a clause would be considered unit if its reduced version is unit. When is a term or a cube considered unit? So I go back and forth between terms and cubes. They are the same thing. A conjunction of literals as opposed to a disjunction of literals. So when is a cube or a term considered unit? If its dual reduced version is unit. There you reduce a term by reducing existential literals, not universal literals. And then there is also a policy you need for how you are going to learn a clause or a cube from conflict. Usually this is through some version of long distance resolution, but you could also do it through Q resolution. Q resolution, I described what it is. Long distance, I'm not going to describe. It's a more sophisticated version. But there is some way of, okay, I have reached this conflict. What clause or what cube should I learn from this and add to the formula? You need an algorithm for that. So if I say that I have a solver based on QCDCL, that doesn't mean that I have already told you what the algorithm is. The algorithm is specified only when I tell you these policies, how they are implemented. All these policies have to be described. And now how can I describe a proof system corresponding to a solver? So from a trace of a QCDCL solver, if a QCDCL solver runs on a formula and finally says the formula is false, and you look at the steps it performed, okay, here I decided something, then I propagated, I decided, I learned, I patch all this together, that patching will allow me to construct a proof which is in Q resolution or in LDQ resolution. Almost all solvers today, their runs will give me proofs in these formal systems, which is why, coming back to the question which you asked earlier, if I have a lower bound in this system, then it means that the runtime will be large. If the solver were also using a dependency scheme somewhere, dependency schemes could be used even by the solver. For instance, when do you decide that a clause is unit? You apply reductions, but do you apply ordinary reductions or D reductions? So various places where dependency schemes could be used. So if you use them, then the formal proof will be extracted in the D version of these proofs, the dependency versions of these proofs. So then you will need lower bounds in these systems. But even if you get so if you get lower bounds in these systems, you have lower bounds on the solver, but this is not an equivalence. Okay, so proof size and solver trace length. This is, in fact, this is some work which I had done with a different set of authors a couple of years ago, where we actually showed instances of formulas where the solver ran on these formulas for a certain amount of time. You analyze the trace, and we produced we saw what was the underlying proof. The underlying proof was in LDQRS. The underlying proof was of polynomial size, but the solver required exponential time to find that. Okay, and this is because it's not just about finding the proof in the formal system. It is about it's not just about the existence of a proof. The solver is a search algorithm. It is searching for the proof. So the fact that there is a short proof does not mean that the solver will run fast. Okay, so ideally, what we want is a proof system which even captures this search component. Just capturing the length of the final reported proof is not adequate to understand where the solver is from. So those proof systems are much more recent. LLCS 2023. I think the conference version was probably 2021. In 2021, this work by Olaf Beiersdorf and his student Benjamin Bohm, they describe proof systems which completely capture everything that the solver does very, very precisely. So it's a very tight connection. So QCDCL style solvers and QCDCL style proof systems. So here the same line has two QCDCLs, but I hope you can see that there's a font difference. So this is the algorithm and this is the proof system. Okay. So you take a QCDCL-based solver, depending on what policies it is using, and then you will get a proof system parameterized by those policies. So they define essentially a family of proof systems, but each of those proof systems was exactly coupled to a particular choice of policies in the solver. Yeah, so that's what I said. Okay, now, so for QCDCL solvers, what is the right proof system? The right proof system is these proof systems defined by these lists. And now, how is the solver actually using a dependency scheme? The solver could use a dependency scheme in pre-processing. For instance, given the formula, first thing compute D, reduce wherever possible, and then run the ordinary solver. Okay, so it's like one pre-processing step, and after that, you don't think about the dependency scheme at all. That's one possibility. Another possibility is to break level order for decisions, and this is what that solver depth QBF did. So I said that normally, if you're trying to decide a variable because you are at a standstill, there is no unit clause, so I have to pick arbitrarily some variable to decide. You can pick any variable for which everything to its left has been assigned. And now this depth order, what depth QBF says is that you can pick any variable if all the variables on which it depends have been assigned. There could be variables to its left which are unassigned, but if this does not depend on that, then the player does not know the value of those variables. So you can break the level order in this. You could use it in reductions to enable more unit propagations. Maybe a clause after applying ordinary reductions doesn't become unit, but after applying D reductions, it becomes unit. So if it becomes unit after D reductions, then you propagate that remaining unit. So that would allow you to do something more than what you could have done earlier. You could also use these dependency schemes in clause learning and cube learning, because the learning policy, which I have not really described, is a construction of some kind of a proof using resolution or Q resolution, long distance Q resolution. So they all have the universal reduction rule. Everywhere you can replace it by D reduction and you will get different. So three different ways in which you could use dependency schemes, and in fact you could use different schemes and different parts. And what we want to understand is how does this actually affect the runtime of the solver. So what we need to do is to take these different ways of using the dependency scheme, plant them into the other QCDCL written in a different font, the proof system, and give lower bounds there. So that's what we did. We came up with this slightly clunky notation. This was the base QCDCL proof system. And now we say, okay, you may pre-process using D. So first do D before doing anything else. Okay. So the dependency scheme, if any, that is used to pre-process, you write. Then when you're actually running the solver, either on the pre-processed formula or on the original formula, what order are you using for the decisions? The default is to use level order, but maybe you use, that's what depth QBF does, and maybe that's what we want to do. So specify what order you use. When do you decide whether, when do you figure out that a clause is unit? You may be using a dependency scheme there also. So the unit propagations, instead of just universal reduction, you may use D reduction. And if you're also adding cubes or terms, the way I described it, I said, of course, when a trail satisfies everything, you should learn a term. But strictly speaking, if you only want to prove that a formula is false, you need not learn a term at all. You can just say that this is not useful for me. And learning terms is absolutely essential if you want to conclude that a formula is true. If the formula is false, learning terms is not essential for completeness, but it can shorten proofs. Even for false formulas, learning terms can shorten proofs. So therefore, we can, if we are concentrating on false formulas, so we can say, okay, maybe don't use cube learning at all. Or if I do use it, then do I use it with long distance? Do I use a dependency scheme? Which dependency scheme do I use there? So I get this kind of big proof system family. And what we did was to show that for well-behaved schemes, those same normal schemes which I had referred to earlier, for well-behaved schemes, this proof system remains sound and complete. We had to show both sound and complete. So it seems like when you add more things, it will remain complete, but somehow adding more things may disable steps which were earlier available. So this was not so hard to show. This was the first, proof of concept that this is a reasonable proof system. It remains sound and complete. And then what do we want? We want to examine actually what is the proof theoretic advantage. So now in 3-4 slides and pictures, I'm just going to show what kind of things we do. So we focus mainly on these two dependency schemes. D standard is the dependency scheme which is used in depth QBF. And there is another solver which I think is called Qt spelled with a Q, Qute, which uses DRS, but it uses it in a completely different way. It assumes that the dependency of the formula is initially empty, and along the way, as it tries to learn it, this is a dependency that I need to add. So it tries to add dependencies as and when discovered. And there it uses DRS as a standard against which to check. But as far as I know, these are the only two schemes which have been used in any solver at all. So we looked at these two. And we try to isolate their impact on each part. These 3 different parts, well, technically 4 here, in which a dependency scheme could be used. So the first thing which we were able to show, which was kind of expected, is that other parameters remaining the same, once you use a dependency scheme to break decision order, this is strictly better. For many formulas, it makes no difference. If at all it makes a difference, it makes a difference by helping. It never makes things worse. But this does not still completely explain why the solver is doing better, because remember, if I can show that in the proof system there is a shorter proof, then it means that there is a run of the solver which can which mimics that proof, which runs in corresponding time. But in some sense, it's a non-deterministic advantage. The solver still has to make the right decisions which match that proof. And a solver has to determinize all the steps at which it has to make decisions. There is going to be some heuristics algorithms driving how it makes that decision. If it has badly chosen heuristics, then this will not happen. For instance, in the case of SAT solver, the propositional world, the big breakthrough which happened in 2010, so 2011, 15 years after CDCL solvers came, the big breakthrough which came was this understanding that resolution is exactly CDCL. Okay? Whenever there is a short CDCL proof, there is a short CDCL run, there is a short resolution proof. This was known. The other direction came about in 2011. Whenever there is a short resolution proof, there is some run of a CDCL style solver which will also be fast, which will be short. But that was non-deterministic. When you looked at practical solvers, they had to use specific heuristics. For specific heuristics, we still had lower bounds. So it's the same kind of advantage that is happening here. It's a non-deterministic advantage. To see it in practice, we'll still need a determinization. And in fact, one way to view level order, so very surprisingly, this paper showed that any order is sound. I mean, forget about level order to dependency order, which we thought, how can you break level order? And they said, you can decide variables in any order. You decide them as and when you want, and then you propagate. Finally, real learning happens when you backtrack. You reach a conflict at the end and then you backtrack and learn something. That is where you have to respect ordering in whatever form, in the reduction, in the de-reduction. The decisions, it plays no role at all. So if that is the case, why aren't solvers implementing any order? I mean, it seems like dependency order gives an advantage over level order. So any order obviously gives an. So why aren't they implementing that? It's because there's too much choice. And if I say, okay, at any point you can pick any variable, okay, but you are a deterministic algorithm, you have to pick one variable. Based on what will you do that? So you would like some advice based on how to make these decisions. Level order is convenient. And it matched the earlier intuition which suggested that level order was necessary. Now we know that it is no longer necessary, but solvers are still mostly sticking to level order. Okay. So level order is a partial determination. Dependency based ordering, it's doing less determinization than this. So it will give rise to more questions about what heuristics to implement. But on the other hand, it is a little bit more deterministic than any order. So it sits somewhere in between. So this is for the order. But what if we restrict to level order? Like I said, most of the solvers do stick to level order. So there, can we say what happens when you use dependency schemes in the other parts? In preprocessing, in clause learning, in propagation, unit propagation. So there the picture is very, very murky. It turns out.
So in the previous, so when we are deciding on a certain order, I mean, in the sense that it seems to be somehow in conflict with what your dependency pairs were, right? Because the pairs were with respect to whatever order. That's okay. So this order is about the decision making.
This order is about the decision making. So this is so in what order? Right now,
an inherent dependency order just based on the prefix. I mean, like basically which comes after what.
Right.
Sort of a
thing. The question is, do you need to respect that? Level order respects.
Okay.
And most existing solvers use level order. So level order is not a complete determinization because it's you look at variables in blocks, existential block, universal block.
Yes.
So if this existential block is fully decided, assigned, then you can choose anything from this block. But which you decide can again make a huge difference.
Yes. Okay.
Right?
Okay.
So it's in that sense, it's a partial determination. And this is determinizing even less.
Then even if it is not assigned, you are
still allowing it. So you are giving more choice for what to decide. Oh, so restricted to level order, which like I said, most solvers are still choosing, even though they know that they don't need to, they're choosing to decide variables in respecting level order. Then the picture is much more messy. And there is this text slide which is difficult to read. Let's go to the pictures. Okay. So here are forces. This system is the standard QCDCL, which is using level order, which is not using a dependency scheme. So not using is the same as saying use trivial dependency. It may be using cube learning, but no dependency schemes. And here are three different ways in which I could use the RRS dependency scheme. I could use it just to preprocess, or I could use it just for deciding when something is unit in propagations. If I use it in propagations, it will also get used in learning. Or I could use it in both preprocessing and learning. So here when I use RRS, here I don't use RRS, you would expect that this is at least as good as that and sometimes better. So certainly we have formulas where any of these three is better than this. Better, these are exponential separations. They require exponential size proofs here, but have polynomial size proofs here. But what was surprising to us, we did not expect it initially, is that the converse is also true. So we also have formulas where these require exponential size and this ordinary system actually runs within polynomial time. So dependency schemes, you would think that they're an advantage, they speed up, enable reductions faster. Is this always good? It's not always good. If you are going to stick to level order in decisions, this can actually be a hindrance. So this was something that we absolutely did not expect when we started, but we were able to show this. So all these dotted lines are incomparable. So even these three different ways of adding RRS amongst themselves, they are incomparable with each other. We can construct formulas which demonstrate exponential separations. This is figure 1. Figure 2 is, it looks like even more messy, but if you think of these three are the triangle from the previous picture but with no cube learning. Those three are the triangle from the previous picture but with cube learning. So with cube learning is always at least as good as without cube. Okay, so that those are these vertical lines. It's always at least as good and it is sometimes better. But what these dotted lines are saying is that the advantage of cube learning could be offset by using a dependency scheme in a different way. So here I used cube learning and I used a dependency scheme for unit propagation. Here I didn't use a dependency scheme for unit propagation. I didn't even use cube learning, but I used it for preprocessing. So if I add the dependency scheme in different ways, where you add it really matters, how you add it really matters. And for each of these pairwise comparisons, we have complete incomparability. Again, these are exponential separations. Yeah. This picture is talking about the D standard policy. D standard policy, there are no systems here which have pre-processing because pre-processing with D standard will never reduce anything. So for pre-processing, it is completely useless. But the other ways in which you could use it, we have some incomparabilities already here, not everything, but this picture is there. And then the final picture is comparing RRS with D standard. Remember what I mentioned earlier that D standard throws away fewer dependencies than RRS. RRS is a stronger, but again we have an incomparability. So sometimes this is better, sometimes this is worse. So it's like I said, it's a nuanced picture. Why this happens? The idea behind many of the separating formulas is essentially this: that we take one formula which is easy for the QBF system, for the ordinary QCDCL system. We take another formula which we know is hard for this QCDCL system, and then we tie them together. So we tie them together in some cleverly chosen way. In one scenario, the level order constraint, it forces everything to go towards the hard part. But even with level order, if I am allowed to use a dependency scheme, then you can jump out of that and quickly go to the easy part. So if I use this dependency scheme, it becomes easy. Without that, it is hard. And scenario 2 is exactly the opposite of that. That the level order constraint allows me to quickly get to the easy part. But if I use a dependency scheme, I somehow get pushed into a trap. There's one example which maybe I will show and then stop. Here is this formula which has some SN variables and it has this formula which is very influential in proof complexity, the pigeonhole principle formula, which says that n plus 1 pigeons can be put into n holes without collision. This you can encode appropriately as a CNF formula, and the clauses of that formula is what I'm writing out here. So I start with this formula, which has only existential variables, which we know is hard for resolution, therefore it is hard for QBF resolution. Then I add for each variable here, I add another mirror variable y here, and I have a universal variable here at the end, and this is one bunch of time together that is being done. And if you see what is happening, if I try to satisfy these clauses, the moment y is set, xi should be set the same way because you can't depend on u to satisfy these clauses. So essentially, this is saying that y has to be equal. Each xi should be the same as that y. So this is the hard part because PHP is hard. And now I have this very easy formula. For every w, there exists a t such that now I have all the clauses on w and t, 4 clauses. But then I stick in a yi everywhere. Okay. And you see that for this formula, the DRRS scheme, which I have not explained, but the scheme staring at this formula will say there are no dependencies. And if there are no dependencies, what happens is that I start off, even when I start in level order, I assign some, let's say y1. I arbitrarily decide y1 should be true. Well, these two clauses get satisfied. These clauses, y goes away and I'm left with w over t bar. I could potentially resolve them, get w and reduce, but I'm not allowed to resolve them. I mean, I'm doing this tray. No, I have to go in order. So the moment I set y, x also gets set, and then I end up somehow refuting whatever is happening in PHP. So if I don't use the dependency scheme, I have to refute PHP. If I use this dependency scheme, I'm allowed to quickly jump to this part which has a constant size proof. So I can get away with a very small proof as opposed to an exponentially long. Okay. That's how the tying together happened. There's another formula where the opposite happens. Let me skip. So I had 3 examples which I was showing here to illustrate how we tie these formulas together. So I think we are already over time. Let me close with this ending slide, the takeaway. So the main thing is that dependency schemes, they're a kind of heuristic which some QBF solvers are using to try to decide QBF truth or falsity faster. And what we have shown is that if they're used to break the decision order, then they can help. But if they're not used to break the decision order, then no matter how else you use them, you will never be able to say one way or the other that yes, this is a good idea or no, this is a bad idea. For some formulas, it's good. For some formulas, it's not. So one obvious question to ask is there more structural information in the formula which can guide us and tell us whether we should use this? We don't really understand that very well. How best to use it even in the decision order, we still need some good decision heuristics. So there is more work there to be done. And finally, this last question here, can dependency schemes be used more aggressively in cube learning? The way I had this very clunky definition of a proof system, but it treated clauses and cubes differently. Part of the reason was that I was only trying to refute false formulas. But also another reason, very important reason, is that for cubes, the long distance cube resolution, if we use dependency schemes, it is not yet known to be sound. For all the other systems, we have soundness, but here we don't even know it's sound. So therefore, it doesn't make sense to tell a solver use it. It may not be so far-fetched, because even for clauses, the solvers used it before we knew that it was sound. It was proved later on. But I don't know any solvers which are using dependency schemes for cubes. As a proof-theoretic question, it is of interest. And if it is shown to be sound, then it may be interesting to see whether any practitioners would actually want to pick up this idea. I do not know. Okay, so that's all I have to say. Thank you.
What is the, sorry, like resolution and proposition of proof complexity, a very basic proof system, which is sound and compute, sorry. What is the analog of that for?
So you can take resolution, which is a proof system for formulas with only existential variables, and then try, say, how do I lift it to a setting where there isn't one answer.
Huh?
There isn't one answer. So one answer is using the universal reduction rule, resolution plus universal reduction. But even there is a zoo of systems. So there's Q resolution, QU resolution, long distance Q resolution, LQU. How do you add it to resolution? There are many different ways. So there's one way using this universal reduction, and that itself gives rise to some 5 or 6 systems. There's another way which says, okay, let me take this formula and somehow expand out the universal variables and then use ordinary resolution. Now this, on the face of it, looks like completely useless. No, you're like trying to take a p-space complete formalism and reduce it to something which is NP-like. There's obviously going to be an exponential blow. But you can do this expansion on the universal variables on the fly. Instead of doing it for the whole formula at the beginning, you pick one clause at a time, only take the universals in that clause and locally expand them and do some resolution and then get rid of. So there is a family of proof systems based on this careful, locally chosen expansion. So that's called expansion plus resolution. Okay. So that is again not one system. Then there is a third type of system on which I gave a talk here several years ago, maybe just before the pandemic. So there is merged resolution, where you try to do ordinary resolution on the existential part, and the universal part of each clause you maintain on the side. What is a partial winning strategy for the universal pair, not for the existential? So that was one system which, so these are all based on resolution. We cannot pinpoint any one of them as the correct analog of resolution.
And for each one of them, we understand, we improve row amounts.
Yes. Yeah, so the proof complexity picture is very clear with respect to this big family of proof systems, but the picture with respect to solvers is not so.
Sorry, one other thing. So actually, can you parameterize these things, like in the sense that suppose how many, so as you said, if there is no alternation, just all existential, then it is our ordinary situation. So suppose I introduce a parameter of how many alternations. Based on that, I want to generalize resolution.
Right, so
So is there a can generalize propositional proof complexity?
so in principle, one should be able to, but it turns out that most of the, not all, but almost all the lower bounds that we know are for bounded alternation formulas.
Oh.
So you don't even need to go as far as p-space to start getting hardness. For instance, even here the formulas that I described, they had some 4 or 5 alternations. They didn't need more than that. So already there is a community, I think in the synthesis crowd, we hear this very often. Sigma 3 is important enough. Can we say more about sigma 3? Something which need not capture the full complexity of p-space, just there, that would already be interesting enough. So many of the lower bounds are for sigma 3 or sigma 4 formulas. Stop sharing.
Yeah.